Let's solve a problem. A 3-meter diameter sphere with a tiny circular surface of size A1 is equal to 2 centimeters squared at its center emits radiation as a black body. T1 is equal to 1050 Kelvin. Calculate the rate of radiation energy passing through a D2 hole with a diameter of 1 centimeter, which is situated on the top of the sphere directly above. Let's assume that the surface A1 emits diffusely as a black body. Both A1 and A2 can be approximated as a differential surfaces since both are very small compared to the square of the distance between them. Given, we have A1 is equal to 2 centimeters squared, D2 is equal to 1 centimeter, D1 is equal to 3 meter, T1 is equal to 1050 Kelvin. Now let's analyze first. Approximating both A1 and A2 as differential surfaces, the solid angle subtended by A2 when viewed from A1. Solution, we have omega at state 2 to state 1 is approximately equal to AN 2 over R squared. It is also equal to A sub 2 over R squared. We know that the formula for the area of the circle is equal to pi R squared. Therefore, diameter is equal to 1 centimeter. Then we convert it to meter. We have 0.01 divided by 2 to get the 0.005 meter as the radius. Then over 1.5 meters squared. Now, the answer will be 3.49 times 10 raised to the power of negative 5 SR. Since A2 were positioned normal to the direction of viewing, the radiation emitted by A1 that strikes A2 is equivalent to the radiation emitted by A1 to the solid angle omega at state 2 to state 1. The intensity of the radiation emitted by A1 is intensity is equal to EB times T1 over pi. It is also equal to the sigma times T1 raised to the power of 4 over pi. Now the value for the sigma is 5.67 times 10 to the power of negative 8 watts per meter squared times Kelvin raised to the power of 4 times to the 1050 Kelvin raised to 4 over pi. And the answer will be 21,938 watts per meter squared times SR. This value of intensity is the same in all directions since a black body is a diffuse emitter. Intensity represents the rate of radiation emission per unit area, normal to the direction of the emission per unit solid angle. Therefore, the rate of radiation energy emitted by A1 in the direction of theta to the solid angle at state omega at state 2 to state 1 is determined by multiplying intensity by the area 1 normal to theta and the solid angle at omega at state 2 to 1. Now, heat rate at state 1 to state 2 is equal to intensity times A1 cos theta 1 times omega at state 2 to state 1. We have the intensity, which is 21,938 watts per meter squared times SR times 2 times 10 to the power negative 4 cos 0 degrees meter squared times 30.49 times 10 to the power negative 5, which is the omega at state 2 to state 1. And the answer will be 1.53 1.531 times 10 to the power negative 4 watts.